So in this video, let's do another normal force example, but this time let's stack some boxes. And I realize I put boxes. We're technically stacking football players, I guess, but we can analyze as if they're boxes to make things easier to understand. So here, during a football game, there's a fumble and 3 players all stack on top of one another. The bottom player is 136 kilograms, the middle player is 100 kilograms, and the top player has a mass of 160 kilograms. So let's first off draw a little diagram here. And in physics and in engineering and any other science, it's always really useful to simplify what your question or system looks like. So my bottom player is 136 kilograms. My middle player is 100 kilograms, so I'll draw him a little bit smaller. So this is 100 kilograms. And then my top player is 160 kilograms, so kind of in the middle. There we go. So this will be 160 kilograms. Now, let's look at these questions. What would the top player's apparent weight be? Now remember, what does apparent weight mean? It means the normal force. So we want to figure out the normal force that this top player feels. So something I'm going to do is I'm going to copy and paste each of these because I'm going to keep reusing this diagram here. So maybe pause the video for a second and draw out all of these a few times. Now let's look at A and let's solve it. So what would the top player's apparent weight be? So our top player is technically using our 100 kilogram guy as a surface. So the normal force here will just be found right there. So there is our normal force of our 160 kilogram player. So his normal force, since he's not moving, equals the force of gravity. And now here, my normal force will be the mass of my 160 kilogram player times gravity. So I can plug that in, 160 kilograms times 9.81 meters per second squared. So my normal force, or my 160 kilogram guy's normal force, aka his apparent weight, will be 160 times 9.81. So the force he's feeling is 1,569.6 newtons up. And let's put that in the proper sig digs. So it looks like 3 significant digits. So 1.57 times 10 to the 3 newtons. And that's going up. Now, if you're confused on how we got to Fn equals Fg, I can quickly run you through that. Currently, our player is just sitting on top of the other players. So he is not moving up or down. So that means he needs another force counteracting your normal force. Because since he is not moving, F net will equal 0. If we figure out what F net is in terms of the forces, it'll be the net force minus the force of gravity. So we have 0 newtons equals net force minus the force of gravity. And then we can add the force of gravity both sides. So I get Fg equaling Fn. And then from there you could solve. So take some time to process what we just went through. And I'm going to move on to B now. So what would the middle player's apparent weight be? So now we're dealing with a little bit more of a trickier question. My middle player here is getting sat on top of by my 160 kilogram guy. So understand that this force the force he's feeling pushing down on him is much greater. So currently, that 100 kilogram guy will feel the normal force. That's his apparent weight. Now what's occurring? I'm going to name these things. This will be mass 1, 2, and 3. So currently, what's pushing down on my surface here? Well, it's the force of gravity 2. Now there's also another force being applied, which is my 160 kilogram force. So there we have another force, which is the force of gravity 1. And remember, this system, the 160 and 100 kilogram guy, is not moving up or down. So something has to counteract those forces, which you hopefully guessed it, is the normal force. So we're going to draw it pretty big to try and be as proportional as possible. So this will be my normal force. So now at this point, remember, F net equals 0. Does it always equal 0? No, it's just because we are not accelerating. And now if we talk about the net force in terms of all of the forces added up together, well, we'll have a net force, or a normal force, subtracting the force of gravity 1, subtracting the force of gravity 2. So my net force, my normal force, minus the force of gravity 1, minus the force of gravity 2. And then from here we can start solving. So this is 0 newtons equals normal force minus the mass of 1 times gravity, subtract the mass of 2 times gravity. And we can start plugging in our values. So this will be the mass of 1, which is the 160 kilogram, times 9.81 meters per second squared, subtract the mass of 2, which is 100 kilograms, times 9.81 meters per second squared. And now we can start plugging these into our calculators. So I'm going to take my calculator out, and I will do 160 times 9.81, which I'm pretty sure I just had on the screen. That's okay. So 1,569.6 newtons, subtract 100 times 9.81. That will give me 981. And now I can combine these two numbers. So negative 1,569.6, subtract 981, and that gives me 2,550.6 newtons. And then from here, we can solve our question pretty easy by adding that number to both sides. So I'm just going to give myself a little bit more room. Okay, so we'll bring it over here. Good. And this should say the force. There we go. Force of gravity 2. So now I can add both sides to this number. So add 2,550.6 newtons. And we will see that the normal force is 2,550.6 newtons, and that's going to be going up, of course. And we can round it to 2.5. Actually, we're going to round it to 3 sigdigs. So 2.55 times 10 to the 3 newtons up. So understand, we just found the apparent weight of our middleman. Okay? Our middle football player feels that heavy. Because if it was just him on top and we got rid of the 160 gram guy, he would feel lighter. But now the 160 kilogram guy, he is putting pressure, he is applying force on top of him, making him feel heavier. So the apparent weight has grown. And thus that is the normal force. Let's do this last question here. What would the bottom player's apparent weight be? How does this compare to his weight? So apparent weight, again, is normal force. So here, what's happening? Well, you have your 136 kilogram guy applying a force of gravity. So again, 1, 2, and 3. So the force of gravity 3. And then you have a force of gravity 2 being applied on top of him. And then you have another force of gravity here being applied from up top. And remember, since this is not moving, we need something to counteract all of these forces, and that will be our normal force, which again is the apparent weight. Apparent weight of 136 kilogram guy. So now we can recall that the net force here equals 0 newtons because nothing is accelerating. And we can determine the equation of our net force based on the forces. So this will be the normal force, subtract the force of gravity 1, subtract the force of gravity 2, subtract the force of gravity 3. And remember, these are all negative because they're all pointing down. This is positive because this is pointing up. Now I'm not going to bore you solving for the force of gravity 1 and force of gravity 2 because we've actually found that up here. Force of gravity 1 is 1,569.6. Force of gravity 2 is 981. So we're going to take those numbers right away and plug them in. So 1,569.6 newtons, subtract 981 newtons, subtract, and now we're going to have to solve this, the mass of 3 times gravity. So the net force here will be the normal force, and we already figured out what this is in our last question. It was 2,550.6 newtons. Subtract, and let's plug in these values. So this will be 136 kilograms times 9.81 meters per second squared. And this will be 136 times 9.81. Oops, let's bring that back here. So this is 1,334.16 newtons, and then we'll bring down our other values. And remember, our net force was 0 newtons, so we may as well plug that in now. And now we can combine these values. So negative 2,550.6, subtracting 1,334.16. So 0 newtons equals the normal force, subtract 3,884.76 newtons, and now we can add that to both sides. So I will get 3,884.76 newtons equals our normal force, which is apparent weight of bottom football player. So being the guy at the bottom of the fumble stack does definitely suck. Football players can probably attest to that one. And let's put this in the proper sig dig, so 1, 2, 3. So we've now entered the 3 times 10 to the power of 3s. So this will be 3.9 times 10 to the 3 newtons up. Now, just to kind of look at this, how does it compare to his weight? Well, his weight was this number here. His weight equaled the force of gravity 3. So his weight equaled 1,334.16 newtons. That was this guy here. So he's feeling a heck of a lot heavier, as we can tell. If we take this number and we subtract it, so if we do 3,884.76 newtons and subtract 1,334.16 newtons, let's just see what the difference is there. So 3,884.76 minus 1,334.16. That gives me, oops, oh boy. That gives me 2,550.6 newtons. So this is how much more he feels he's heavier. Let's take that number and divide it by what his original weight is, 1,334.16 newtons. So if I divide this by 1,334.16, and then I times it by 100, he feels, so I times this by 100%, he feels 191% heavier than he normally does. He feels 191% heavier than normal. So that's just something interesting to think about. We weren't asked to do that part of this question, but it was something to just think about. So his apparent weight is found here. And now we can see how to find a bunch of different apparent weights with objects stacked on one on top of each other. If you have any questions, let me know.